Eddie Inak, currently at the Institute for Advanced Study, formerly at Rutgers, right here in the CS department, and studying this fall at Purdue University. It's a pleasure to have Eddie come back. Also, Eddie was the previous Matthew Russell. He is one of the former organizers of this famous seminar. As usual, we're going to take the speaker to dinner. If you'd like to join us at the usual place, let me know immediately after the talk. And reminding you, no electronic devices allowed in the seminar. Thank you.
Thank you, Dr. Z, for the invitation. Thank you. It's always a pleasure to be at the Experimental Math Seminar, even more so as a speaker. So thanks. I'm going to be talking today about a combinatorial approach to hypermatrix algebra. And this was very much inspired by a paper that Dr. Z written about a combinatorial approach to matrix algebra. So I would emphasize the connection by slowly warming up. And I invite questions at any point during the talk. The results are not too hard to prove once you get the idea. So here's the plan. We're going to quickly go from matrix product to hypermatrix product. And we want to go to hypermatrix product. And then the second thing we want to discuss is going to be the combinatorial lens at linear algebra. And finally, hopefully we get to the Cayley-Hamilton theorem. And if I can make it this far before the 48 minutes, we could discuss even more. As I said, questions are welcome at any point during the talk. All right, so let's warm up by reviewing matrix multiplication, and by no means insulting your intelligence. It's merely to emphasize the combinatorial depiction. So if you think about matrix multiplication, here's a mnemonic device I use, which is helpful to remember it if you forget it, but more importantly, it actually facilitates the digestion of the generalization. So typically, here's as I start. I want to compute the entry CMN. I'm going to write sum over k. Let me start at 0. And here's the typo I'm going to make on purpose. And then what I say to the students is cross out this n and change it into a k. And cross out this m and change it into a k. Okay, so note that I did not cross the same index. I started here, I made an arbitrary choice, but I crossed out the second index here, and here I crossed out the first index. All right, you could have defined matrix multiplication by crossing out the first index and crossing out here the second, but you would have flipped the order.
Yeah, so what's capital K? Yes.
So K is the index. So let me say something about the matrices.
Capital K.
So capital K is the number of entries. So in the case, so for example, the matrix A is capital M by capital K matrix, and the matrix B is capital K by capital N matrix. It's just to help the indexing. So little m is going to go all the way up to capital N. Little m is going to go all the way to capital N. Okay, so a gadget construction which is useful in teaching linear algebra is the following. So I'm going to pass this around. This just merely emphasizes that the location of every entry in the answer is sort of an intersection of two rays. One coming from the rows of A, and one coming from the columns of B, and every entry is sort of identified by this scheme. Okay, so this is useful, and you would see why in a second. You can pass this around. Now the point is, let's use this mnemonic device to suggest how we would naturally generalize matrix multiplication. So instead, I'm going to write this. dm_p is going to be sum over k, less than capital K is equal to 0. And I'm going to make the same mistake again, a_m_p, b_m_p, c_m_p. This is ternary. Let me erase here. So let me erase this second guy just by mimicking what I did there. Change this into a k. Since I have to not do it for the same index, I'm going to change this guy into a k. And here, the first one is going to turn into a k. Okay, so here I'm saying that if you want to do the product, which is noted this way, D is circle of A, B, C. A is a capital M by capital K by capital P. B is a capital M by capital N by capital K. And C is capital K by capital N by capital P. So just as for matrices, there are constraints which tie the matrices you can multiply, namely the number of columns must match the number of rows. Here there are constraints which tie these, let's call them for the sake of the conversation, rows. These guys are going to be columns, and these guys I'm going to call them depth. I'm going in the depth direction. So there is a connection relating the three of them. The k here must be the same, but there are also pairwise constraints. The m relates only A and B, and the n relates C and B, and finally P relates A and C. Now this seems somewhat artificial. Can I come up with a gadget that is analogous to the one I sent you? Unfortunately, you can. It's slightly more involved, but it's fun to see for once. So let me show you what the gadget looks like. So it looks like... Sorry, you will get this passing around. So you can see in the gadget for matrices, one of the dimensions is cheated. There's nothing coming from the depth direction. So the way you want to think about this is what I want to compute. This is D. And D is sort of squeezed out by three hypermatrices. All right, so right. And here's what you should think about. In the matrix case, you had these two. I don't know if you can see them, but in the matrix case, you had two of them. You didn't have the third dimension to play with. In other words, you had A and B, but you didn't have this C. The C is the one on top. So you should think about them as each one of them feeding some sort of lasers. And fortunately, I have some visual depiction of those. So let me pass these around. These are supposed to depict the cubes, so you get to see them for yourself. And you have the figures to pass around as well. All right, so this can pass around. So the point is that the first A is going to feed rows. B is going to feed depth, and C is going to feed columns. And what is interesting is that if the entries of A, of B is completely 1, you go back to matrix multiplication. So matrix multiplication is a special case of this product. All right.
One question.
Sure.
So, you know, there's more comment, but like the order that we put the K's just doesn't feel natural to me.
Yes.
Like I'd rather put like the K in the third slot for the A, the second slot for the B, and the first slot for a C.
So you would want to put the K here?
Yeah, like 3, 2, 1. So you know, because like 2, 3, 1 feels awkward, I guess.
So definitely the argument here is that would have been perfectly valid as well.
Okay.
There's an arbitrary choice you have to make And when we wrote the paper, this was what felt natural. But there's no reason for picking one and not picking the other, as long as you're consistent.
Okay.
So for the purpose of this conversation, this is what we did. But really the motivation for me was, here I crossed out the second one, so I wanted to cross out the second one here. And the last one, I crossed out the first one, so for the last one, I also wanted to cross out the first one. But this is just for me saying, if B was all 1, then I recover matrix multiplication.
Okay.
Right. Yes?
Does this have a history at all in terms of
Yes.
tensor contraction?
Yes. And I should say this. This is very important point. So this does have a history. This multiplication was proposed in the 90s by Messner and Bhattacharya. So Messner and BH Bhattacharya. In the 90s, actually suggested this multiplication. And this came out as they were studying what's called in combinatorics association schemes. So association schemes is this field of combinatorics which actually comes from statistics, where you want to design an experiment and partition the samples so as to minimize the bias you introduce. And it came from very practical field of agriculture. They wanted to partition the land, try a different experiment, and they did not want to introduce bias by their partitioning scheme. So how should you partition your experiment? The design of the theory, which was proposed by Bose back at the time, heavily built on properties of finite fields and matrix algebra. So matrix multiplication is tied to the study of association schemes. But association scheme historically been studying pairs. You partition and you study the influence of pairs. And what Messner and Bhattacharya wanted to do in the 90s was to study association scheme of triplets. And very naturally, they was led to this multiplication. Though be it, they made a different choice of convention. For example, they deleted this guy. This is the first K, and so on. However, we did not know about this when we started working on the topic. Now, association scheme are combinatorial object, and I promised a combinatorial depiction for what we're going to do. And the combinatorial understanding is not going to be via association scheme. It's going to be via graph theory. So let's get into the graph theory part of the picture. To get a sense of how you go from matrices to graph, this was suggested by Danish Koenig. And he suggested a construction known as the Koenig bipartite directed graphs. And what a Koenig directed graph is for a matrix A, which is, let's say, capital M by capital N, you construct a bipartite graph with n vertices, say R0, R1, all the way up to R, capital M minus 1. These are vertices which are identified with the rows of the matrix, and you have vertices that you identify with the columns, C0, C1, all the way up to Cn minus 1. And every entry of the matrix, let me write here Ri, let me write here Cj. Every entry of the matrix is an edge which goes from the rows to the columns. So this is a complete bipartite graph, and the edges going from R0 to R1 are labeled by entries of your matrix. So this is entry ij. What's convenient with this graph as opposed to the adjacency matrix graph, adjacency depiction, is that you can encode rectangular matrices without worrying. And what an adjacency matrix does is really identify these two vertices together. So if you had a square matrix, then you can say, well, I'll identify C0 and R0, and you're back to the adjacency matrix depiction. Now, this was studied in combinatorics, and most of the discussion in Dr. Z's paper was about the properties you can derive from this. How you could depict the Cayley-Hamilton theorem using properties of graphs. So now that we've defined what it is, how we go from a matrix to a graph, what does this have to do with multiplication? How do we understand matrix multiplication using these? So since I came early, in the interest of time, I did these drawings, and they happen to be useful. So you depict A, in the case of 2 by 2 matrices, you depict A as a 2 by 2 matrix. So it's going to have 2 rows, 2 columns. B, in red here, is going to be also a 2 by 2 matrix. And to do the multiplication, Koenig suggested to do this identification scheme. Column 0 is going to be identified to row 0. Column 1 is going to be identified to row 1. And now the result of the matrix multiplication was, if you wanted to know entry 0A or C, 0, 1, you had to look at the contribution of all the paths, which leave 0 and end up at 1. And if you're going along a path, you multiply the weights of the edges that are on the path. All right? So this was the Koenig gadget construction for doing matrix multiplication. And you can see here why, when you compute A squared, you're saying something about paths of length 2. And if you're computing A's cubed, you're saying something about paths of length 3. Really, because you're gluing these graphs together. So what I want you to do is think about, instead of think about path, think about triangles. Every term in the product, let's think about it as building a triangle configuration, where the back edge is the result of your multiplication. So if you wanted to compute the entry 0, 0 of the product, you would have to add this triangle configuration, which is A0 times B0, and you would add this triangle configuration. Now, you can see already that matrix multiplication sort of involved these sort of tripartite graphs. And these tripartite graphs induce natural 3 uniform hypergraphs. So you have triangles instead of edges if you look at this configuration. So if we wanted to define a Koenig-directed graph for a hypergraph, here's what we would do. So given a hypermatrix, given M by N by P hypermatrix. And what I mean by hypermatrix is essentially this block of cube that you have. 3-dimensional array of numbers. You can associate with it a tripartite 3 uniform hypergraph. So consider the tripartite directed 3 uniform hypergraph. And here, naturally, what you would do is something very analogous to what we did here. You would have a collection of vertices for the rows. Row n minus 1. You would have a collection of vertices for the columns. C0, C, n minus 1. And you will finally have another collection of vertices for the depth. D0 all the way up to D, P minus 1. And the point is that entry ijk of your hypermatrix is going to be a triangle, a directed triangle in your 3 uniform hypergraph. Now this looks quite similar to this. And the theme is going to carry. If you know how to multiply, how to interpret this combinatorially, it would give you a combinatorial interpretation for multiplying hypermatrices of order 4. And that's easy to see once we see the picture. So how many, given our hypermatrix for this to work out, let's check how many hyper edges can we have in our 3 uniform hypergraph. Is it clear how many hyperedge we can have? How many triangles can we build?
M and P.
Exactly. And M and P corresponds to the number of entries. So we have a bijective proof that we can indeed associate these guys. Now the question is, how does this tripartite graph, which we want to think of as a generalization of this, how does that relate to the multiplication operation which we described? What's nice about the conic directed graph is that matrix multiplication amounts to this identification scheme, which allows us to understand the edges of the result as paths. Now, a similar thing can be done here. If you have triangles that you're identifying, well, it turns out you're building tetrahedrons. So in the other case, we were building paths. Here you're building tetrahedrons. And to see how you build a tetrahedron, consider a hypergraph which had only one non-zero entry in A, one non-zero entry in B, and only one non-zero entry in C. And let's assume that non-zero entry was for some value of k, so I can erase this sum. You only have one non-zero entry for a specific value of k, then the product, the answer, is going to be the product of these three numbers. Now, look at what happened. We're saying that the vertices M and M have to be identified. We're saying that the vertices P and P here have to be identified as well. And finally, we're saying that N, so you have N here and N have to be identified. And what you're actually doing is building this triangle MNP. And this K, the red guy, is where these three tetrahedron meet on the top. Right? So every term in here, just as in matrix multiplication, every term is the triangle configuration. Every term in this product is building a tetrahedron. All right? So the combinatorial interpretation here is going to help us, because if matrix multiplication allowed us to count paths for graphs which had 0, 1 entries, this multiplication is going to allow us to count how many tetrahedral simplices we have. Okay, so let me pass this around so you can see. Now, there are properties of this algebra which are convenient or inconvenient depending on how you want to look at it. First of all, it's not associative. So if you multiply hypermatrices, the parenthesization scheme matters. And the way I think of it is hypermatrix multiplication breaks the symmetry in the parenthesization. And this turns out to be useful. If these tetrahedral simplices that you build, they actually allow you to build very specific objects. So suppose I wanted to build this simplex. This is a tetrahedral simplex that I build by gluing one tetrahedron onto another. And this corresponds to a very specific parenthesization scheme for building this. And I'll write it down. So suppose I wanted to build this by gluing triangles. How should I do the sequence of products? If I wanted to build that shape using the minimum number of triangles without degeneracy, here's the number of multiplication and the sequence of multiplication I would need. So I would need 7 by 7. So A, B, C, D, E, F, G, H, I are all 7 by 7 by 7 hypermatrices. Okay. More importantly, the only non-zero entry of A is A562. So let's put this symbolically. Everything else is 0. The only non-zero entry of B is B516. So by the way, this is hard to figure out. It's not, if you don't have a computer, it could take a while. But once you know how it works, it's easy to find out. So C has only 612. D has only 352. E has only 315. F has only, the non-zero entry is 043. G, sorry, it's almost done, 014. H is 413. I has only 032. And the sequence of products that you have to make is exactly this one. Let me write it here. It's the following sequence. So we're going to multiply I with the result of F, G, H. The whole thing has to be multiplied by DE and A, B, C. 1, 2, 3. All right. Any other thing you do, you get 0. You get the all 0. So the sequence says, first do ABC. Once you're done doing ABC, you have the tetrahedron coming from ABC. You're going to glue that to DE, to some face of DE. And then the results, you have to build this tetrahedron independently and glue the whole thing together to one of the faces of I. And this is exactly what you hold. So the point is that if you do these sequence of products where you do the parameterization scheme matter, you're actually building simplices and you're counting how many simplices there are. Now,
so this is a 7 by 7 matrix.
Yes.
One non-zero entry.
Exactly, only one non-zero entry. And the non-zero entry is the product of all these variables. Right. Everything else is 0. All right, so now we pointed out that you can build tetrahedral simplices, and if your hypermatrix was zeros and ones, you're counting the number of tetrahedral simplices that you can build. So now we sort of boil down the pieces for expressing a Cayley-Hamilton theorem, and I think we have enough time to cover our basics. All right, so let's quickly review what Cayley-Hamilton says for matrices and how one could think about it. Cayley-Hamilton is this very fascinating theorem which essentially argues that if you took the sequence, you start with a matrix A. Let's say that the matrix has real entries and it's an n by n. Cayley-Hamilton says if you took the sequence of powers a to the k and you went up to n squared. So let me here, I want to be... Now, so you know by the fact that A is an n by n matrix, it has n squared entries. If you pick n squared plus one of them, they must be linearly dependent. But Cayley-Hamilton says more. It says that n plus 1 suffice. If you take a sequence of powers, right, so the span, let me write it. So the max dimension of the span